Hello everyone. Today we will start a new chapter about the refraction of light. Well, did you ever notice how a spoon looks bent when dipped in water? Or why a pool seems shallower than it is in reality? Or why this duck, for example, here looks weirdly cut into two parts? Well, there is no magic involved. It's all about the science of refraction. Today, we're going to dive into the world of light and discover how it bends and changes its direction as it travels from one transparent medium into another, like air, water, or glass. This isn't just a textbook stuff. It's happening all around you, every day, and wherever you go. So I need you to grab your thinking caps and join me on this awesome science adventure. Let's get started and unravel the mysteries of refraction together. So, by definition, the refraction of light is the bending of light or the change in the direction of propagation of this light as it goes from one transparent medium, like air, into another transparent medium, like water, for example, that has different optical properties. And of course, the reason of this change in the direction of propagation is the change in the speed of propagation. So when light is going through air and then passes into water or glass, its speed will change. And this change in the speed will cause a change in the direction of propagation of the light. And this is what we call refraction. Now, what is the physical property that affects the speed of propagation of the light? This is what we call the index of refraction. Index of refraction, it is a property that affects the speed of light as it goes from one medium into another. Now, by definition, the index of refraction is nothing but the ratio of the speed of light in the vacuum, denoted by C, to its speed in the given medium, denoted by V. So we get the following formula. N is equal to C over V, where N, of course, is the index of refraction of the medium. We have C, which is the speed of light in vacuum, and V is the speed of light in the considered medium. And we noticed that these two speeds are expressed in meters per second, of course in SI units. And since we are dividing two speeds on each other, of course, the index of refraction will be then a unitless quantity. It doesn't have a unit because meter per second over meter per second will cancel out. So the aim of finding the ratio of the speed of light in vacuum to the speed of light in the given medium is to compare these speeds. For example, we know the speed of light in different materials. Of course, you have the speed of light, as you can see in this table, the speed of light in air, which is, or vacuum, of course, approximately the same, which is considered to be equal 3 times 10 to the power 8. Of course, you need to be familiar with this number. Then you have different speeds in different mediums. Now, what if we needed to find out the index of refraction of water? So we simply apply the formula. Remember, to find the index of glass, we just calculate the ratio of speed of light in vacuum, C, over its speed in the given medium, which is glass in this example. So by substituting each term by its value, as you can see, 3 times 10 to the power 8 over 2 times 10 to the power 8. So we will get in the index of glass, which is equal to 1.5. Of course, this means that the ratio of the speeds of light is equal to 1.5. For example, we can say that light in vacuum is faster than glass by 1.5 times, or the speed of light in vacuum is 1.5 times the speed of light in the glass. Now, before proceeding to the laws of refraction, we need to be aware of the refraction diagram so that we can be familiar with all the terminologies that we will be using in this chapter. So first we have the source of light. For sure, the source of light will send a ray that we are going to call an incident ray. So the ray that gets out from the source is always called incident ray. And the point where the light hits the surface, we call it point of incidence. Of course, here we are dealing with two transparent mediums, but always we will have some reflection. That's why here we have a partial reflection. Like for example, when you look on the surface of water, you will always see your reflection. So this reflection, of course, is not a total reflection like the mirror. So we call it partial reflection. And for sure, most of the light will go through the other medium. Here, this is the refracted ray. Of course, the refracted ray is the bent ray. We are going to call it IR. Then always we need to draw the normal. The normal, which is the perpendicular to the surface of separation at the point of incidence. Remember, guys, in physics, whenever you hear the word normal, it most probably means the perpendicular to the surface. Next, we have the angles. Now, of course, we have the angle between the normal line, between the incident ray and the normal line. The angle between them, we call it the angle of incidence. Always, guys, whenever they ask you about the angle of incidence, make sure to know the position of your normal and the relative position of the ray. And the same thing down, we have the refracted ray and the normal, where the angle between them is called the angle of refraction. Of course, you may pause the video to draw your diagram using your nice ruler, of course. Then, after that, we may start checking the laws of refraction. Now, after finishing our refraction diagram, let's proceed to the laws of refraction. Now, the first law, as we can see in this diagram, the incident ray, the refracted ray, and the normal line, we notice that they all lie in the same plane. They all lie in the same plane that we call plane of incidence. So this is the statement of the first law of refraction. So again, the incident ray, the refracted ray, and the normal line at the point of incidence all lie in the same plane that we call plane of incidence. Now, let's proceed to the second law of refraction, or what we call Snell's law. In order to investigate this law, we're gonna use a simulation, a PhET simulation that will help us investigating this law. So we will choose our source of light. So that will send an incident ray and will show the refracted and the partially reflected ray. We will choose first our first medium, which is the air of index of refraction 1, as you all know. And then we'll choose the second medium, in this case water, of index of refraction 1.33. And obviously here, water is said to be more refractive than air. Then in order to measure the angles, we are going to choose our protractor that shows it's 0 in the middle. It will help us in measuring the value of the angle of incidence and refraction. Obviously, we need to see the normal. As you can see here, we have our normal. We will start varying the values of the angle of incidence to check the corresponding angle of refraction, and then tabulate the values to investigate the law. So, first of all, this is our angle of incidence. In this case, it has a value of 20 degrees between the incident ray and the normal line. As you can see, the angle between the refracted ray and the normal in this case is equal to 15 degrees. So this is our first measurement. Now we will shift a little bit. Yes, here the angle of incidence in this case is equal to 30, and again the angle between the incident ray and the normal line. Then we will go down to check the value of the angle of refraction. The angle of refraction in this case between the normal and the refracted ray, as you can see, it has a value equal to 22 degrees. Then let's choose a third value for the angle of incidence. This time we will choose the value of 40 degrees. Of course, the value of the angle of refraction that corresponds to an angle of incidence of 40 degrees will be different. So here we can see that it is equal to 29 degrees approximately. Next, what we are going to do, actually we are going to find the ratio of the sine of the angle of incidence to the sine of the angle of refraction. If we do this in the lab, we will notice that all these ratios are the same. In other words, the ratio of the sine of the angle of incidence to the sine of the angle of refraction is not changing. And at the same time, the ratio of the indices of incidence of the second medium to the index of the first medium also is not changing, and they are all equal to a specific number. In other words, this ratio is constant. And again, after analyzing the values that we got in this table, it is obvious for us that the ratio of the sine of the angle of incidence to the sine of the angle of refraction is constant and is also equal to the ratio of the indices of refraction over each other. In other words, n2 over n1 is also equal to the same value, in this case 1.33. Keep in mind, guys, this value 1.33 works only for the given mediums, in this case air and water. If we change the mediums, of course this value will change, but for the same mediums always we will get the same constant value. Hence we can say that sine I over sine R is equal to n2 over n1, and by cross multiplying we can get the final expression of Snell's law that will help us in solving the refraction problems, which is n1 times sine of I is equal to n2 times sine of angle R, which is the angle of refraction.
Thanks for your attention. See you in the next video.